Okay, in this video we are going to talk a little bit more about solubility, some variables that can impact the solubility, and we're going to look at some solubility curves, okay? So when we talk about solubility, right, we talked about solutes and solvents in the last couple of videos. So the solute is what I am dissolving, and the solvent, for the most part, is going to be water, and it's what I'm dissolving my solute into. So you should kind of know by now, just from experiments you've done in middle school, where you looked at like usually dissolving sugar or dissolving salt, and usually you heat your water, that changing the temperature of water is going to change how much solute is able to dissolve, okay? So generally when we talk about solubility of something, we are going to give it to you in a way that looks like this. We're going to tell you that the solubility of a chemical is some number of grams per 100 mils. So that means if I have 100 mils of water, I can dissolve 36 grams in it, okay? It's always going to specify a temperature. And the reason they're going to specify a temperature is if I change the temperature, I am going to change the solubility of that particular chemical, okay? It might go up, it might go down, but it is dependent on temperature, which is why we always specify it. So what we find is how the solubility is going to be impacted by temperature is dependent upon the state that that compound or solute is. So our solids, liquids, and gases are going to respond differently to changing the temperature, okay? And part of why they're going to respond differently is different things have to happen, right? So we said that for a solute to be able to dissolve into a solvent, we had to break the attractive forces holding the solute together. And what we find is, depending on the state, the attractive forces are going to be different. So if I have a solid, my molecules are all kind of tightly locked into place. They might be able to vibrate a little bit because we always have motion for our molecules, but they're stuck in place because there's really strong attractive forces to all the things around it. When we move to a liquid, the attractive forces are a little bit weaker. So they're able to form them and break them and form them and break them, right? That's why I can take water and I can pour it. When I move to a gas, there isn't really any attractive forces. My molecules are going crazy and they're all over the place. So what we find is for a solid, when we increase the temperature, we're going to increase the solubility. And the reason for that is we're giving those molecules more energy and they're able to break the attractive forces that are holding the solute together. Okay, so this is why as we increase the temperature, the solubility of a solid is going to increase. We give it more energy, it's more able to break those attractive forces, so more is going to be able to dissolve. If we think about a liquid, it's already able to break those attractive forces. So changing the temperature is not going to impact the solubility. We're going to find that it's going to remain unchanged. Gases, on the other hand, are actually going to do the opposite. And that's because it has nothing to do with breaking attractive forces. They've already completely broken them. It more has to do with the fact of, for gases to dissolve into water, they have to go into the solution, and they have to stay in the solution. So it takes energy for those molecules to be able to break free from that solution. And the hotter we make it, the more energy we give our molecules, and the easier it is for them to break free from the solution. So for liquids, no impact on temperature change. For solids, the hotter it is, the more soluble it is. For a gas, the hotter it is, the less soluble it is. Okay, so you got to be aware that they do behave differently depending upon the initial state of that solute. So next factor is pressure. Pressure is only going to impact the solubility of a gas, okay? So if you think about opening a pop can or a pop bottle, as soon as you open it, you decrease the pressure. And then all of a sudden you see that all these gas molecules come flying out of your solution, right? That's the fizzing that you hear when you open it. So what happens is, at high pressure, which is what's happening inside of my pop can before I open it, the gas molecules don't really have anywhere to go, so they have to go into the solution, so I increase their solubility. But as soon as I open it and decrease the pressure, there's so much room for them to go, they're all going to come out, okay? So gases, high pressure, high solubility, low pressure, low solubility. So solubility curves are something that we look at. So a solubility curve is generally going to have multiple lines on it. Okay, it's going to have over here grams of solute per 100 grams of water. So this is telling me how much of that particular chemical will dissolve in 100 grams of water at a specific temperature. Right, and down here we have our temperature. So you're going to find that most of these curve up as we increase the temperature. And that's because the majority of these are solids, and that's what we expect solids to do. Right, ammonia is a little different. Ammonia is a gas, which is why we find that its solubility decreases as we increase the temperature. And this right here, this is an exception, the cesium sulfate. It does something that we don't expect it to do. It's a solid ionic, but as we increase the temperature, it decreases in solubility. Okay, we're generally not going to ask you to like memorize any types of exceptions. Usually we're going to ask you to be able to interpret a curve like this or to recognize where something is doing something that it shouldn't, right? So that would be recognizing that this here isn't doing what it's supposed to do, right? It's an ionic, it should be a solid at room temperature. We would expect that solubility would increase as the temperature is increasing, but it's not doing that, okay? So questions we will often ask you. So a sample question that we could ask you about this usually has to do with what happens to the solubility as we change the temperature. So you could get a question that says, a saturated solution of potassium nitrate at 80 degrees is cooled to 30 degrees C. Type in the right buttons, get on. So how much solute will crystallize out of a 100 ml solution? So what we're going to do, so we need to find the potassium nitrate. So here's potassium nitrate. So that means this is the curve that I want to be looking at. So 80 degrees, oh, okay, I picked too high temperature. It goes off the chart at 80 degrees. So let's maybe change that from 80 degrees to 70 degrees so that it's actually on our chart. Okay, so 70 degrees, I'm going to look at it. The potassium nitrate is probably right around here. So we're looking at 130. So that's how many grams of potassium nitrate I could dissolve in 100 ml of solution or of water. So now we cool it to 30. So 30 is here, and we're going to read up and come across. Okay, definitely open to some interpretation because you are reading a graph. So 30 degrees of potassium nitrate, I don't know, I'd probably say that it's around 46, let's say. So how much is going to crystallize out? Well, I had 130 that was crystallized in. Now I've cooled it. Sorry, that's an awful looking 6. Let's make it look more like a 6. And now only 46 can be in there. So we're going to do 130 minus 46. That tells us that 84 grams are going to crystallize out. Okay, so it comes down to what's the difference between the two of them. Okay, the only way we're really going to sometimes change this question up is we are going to change what the volume is. So instead of 100 mils, maybe we'll say it's 50 mils, right? And then I'd have to be able to recognize that I need to have all of these numbers because these numbers are for 100 grams of water, and now I only have 50, right? And if I told you it was 200 grams of water, you'd have to double what those numbers were. Okay, and you'll see that as you work through your workbooklets. You do definitely have a couple of assignments in there that do involve solubility curves, and you'll get to practice that a little bit more. Okay, so after that, we kind of revisited dissociation equations, right? We saw that in the last lesson. So make sure you're paying attention to whether it's saturated or unsaturated, so use the appropriate arrows, right? So we're going to use a single-headed arrow if it's, that should say, oh wait, no, I'm not actually reading the question. It says a single-headed arrow is used unless it is a saturated solution. Then you get to use a double-headed arrow. Okay, if it doesn't specify, always assume that it is unsaturated and you are going to use that single-headed arrow. Okay, and you're going to break it apart into the ions just like we saw in the last video. And then also in the last video, we talked about ionization equations. So the difference between dissociation and ionization was these are going to be for acids. So we're going to make sure that we include the water in our equation instead of putting it over the arrow. example we looked at in the last video was for HCl. And so what you're actually going to find is that for acids, there's also a little bit of an exception or difference as well. And that has to do with how many hydrogens I have. So if the acid has one hydrogen, you can write the equation the way I showed you in the last video, and I only showed you that one because we were starting out simple. What you're going to find though is if it has more than one hydrogen, so let's say I have sulfuric acid, which is H2SO4. This is actually going to require two ionization equations, and that is because it has two H's. What am I pressing? Random buttons. So we're going to do this plus our water. So far it all looks the same. Okay, we're going to put our air out. When we break this apart, we're going to break it apart. We're still going to have the water over here. But now, this has two H's. I only get to take one H off at a time. So the first H is going to come off, and it's going to give me a hydrogen ion. So if I had sulfuric acid, which was H2SO4, and I just took one H away, there is still one H left. So I'm going to have plus HSO4 minus, and it gets one minus charge because I took one hydrogen away. Okay, if you look in your red data booklet, I'm trying to see if I have one around me to show this to you. You're going to find that these things are also in there, right? Remember we talked about how there's that acid table at the back. So if you look closely at your acid table, try to center it the right way, you're going to see that it has H2SO4 in here, somewhere over here. I can't tell because I can't see. And then right next to it is the HSO4 minus. So that's how you know that's what you're turning it into. Okay, step 2, I'm now going to take this HSO4 minus, and I'm going to start with that. So I'm going to have HSO4 minus AQ, and I am going to react this with water. Okay, so this is my second step. Now I'm taking that second hydrogen off. So product-wise, I'm going to have water. Oh. And then I'm going to take the hydrogen off of here, so plus an H plus. Plus, so what's left once I take this H away? Well, I just have that sulfate, so SO4 2 minus aqueous. Oh, I missed the end of the bracket. There we go. Okay, so two hydrogens, so two ionization equations. Equation 1 takes the first H off, equation 2 takes the second H off. Okay, if I had something like phosphoric acid, which has 3 H's, there would be 3 steps to write, 1 to take each hydrogen off, okay? So that's a little bit different with the ionization equations. So now in your booklet, you should be able to finish off that first intro assignment. You should be able to work through the 2 solubility activities, and you should be able to start on that ionization and dissociation equations sheet that is also in there, okay? And then the next video, we're going to start getting into some of our calculation pieces.